Welcome to the Digital Seminar Series organized by the Statistics Assessment and Data Management Core, a part of the HIV Center for Clinical and Behavioral Studies at the New York State Psychiatric Institute and Columbia University.
Hello, my name is Martina Pavlicova, and I am an associate professor in the Biostatistics department and the director of the Statistics, Assessment, and Data Management Core in HIV Center. Today, I will talk about correlations, what they are, and what exactly they measure. Gail Basaraba and I created the talk together. I will start with explaining or defining what is an association and how we measure it. We will talk about Pearson correlations, pros and cons of Pearson correlations. Then we will introduce Spearman correlation and modern graphical representations of correlations. So what is association? Here is an example. For instance, we have heights and weights of sample of 14 students, as you can see in the graph. Do you expect a relationship between these two? Association is a measure of relationship commonly used between two continuous variables. For instance, we can see a relationship between two variables if knowing one value or one data for the one variable, we can estimate the other variable. Here, if we know that the person is tall, we can actually estimate the person's weight reasonably well. Because here in this graph, the data go up, as values on x-axis increase, the values on y-axis are also higher. This association is called positive association. So we have positive associations when higher values for one variable correspond to higher values for the other variable. We can also have negative associations when higher values for one variable correspond to lower values for the other variable. Because two variables play a role in associations and correlations, we have names for them too. We distinguish between so-called explanatory variables, which are sometimes called independent or predictor variables, and those are usually plotted on an x-axis, and response variables, sometimes called dependent or outcome variables. Those typically go on y-axis. Those are the variables we would like to estimate. So in this graph, height is the predictor variable and weight is the outcome variable. Knowing the height of the person from the same population, we can then estimate the person's weight. So associations help us to using associations, we can estimate one variable using the other variable. So for instance, in this example, suppose we know that a student is 60 inches tall. Based on the scatter plot, how much would you expect the student to weigh? So if you look at the scatter plot and you find height 60 inches tall, we can actually go up and see where the 60 inches sort of intersect with the imaginary line in the data, and we can see that a student 60 inches tall would weigh about 160 pounds. So the range of value in vertical slice around 60 inches tell us also something about variability in the outcome way once we have taken x into consideration, the height. Here, we can see the variability around the imaginary line is actually pretty small, so we can talk about strong positive association. Very often when we talk about associations, we use words as strong, moderate, weak associations. However, it's very hard to compare when different people consider different associations strong and weak. So that's why we have actually a correlation coefficient that gives us a numerical summary of linear association between two variables. Scatter plot then gives us a graphical representation of the relationship. The correlation coefficient, which we usually compute, then measures the strength of the linear relationship between two variables x and y. Because it's a number, as a number, it has two characteristics. One characteristic is a sign, and the sign of every number can be either positive or negative. Negative sign means or denotes a negative association. As x increases, y decreases. Positive sign then means positive association. As x increases, the y increases also. The correlation number then, the magnitude of the number, can be between -1 and +1. Around -1 we have the strongest negative associations. Those are the associations when knowing x gives us almost perfect estimate of y. Close to 0 we have very weak associations, almost no association, where knowing x doesn't give us very much information to estimate the y. And then close to +1, we have a strong positive association, and again, knowing x, we can quite well estimate the y. Correlation coefficient is never smaller than -1 or larger than +1. It is always between -1 and +1, and it's never interpreted as a percentage. Pearson correlation coefficient then is computed using the formula on the slide. You can see that the formula utilizes averages of x bar, averages of y bar, and it's basically a combination of the squared differences of each data point from its own average and then summed together. Most of the times we use computers to compute correlation, so we don't really compute it by hand. So what are the pros of correlations? Why correlations are so popular? Well, first of all, correlation is unitless. For instance, the correlation between height and weight, when computed in inches and pounds, will be the same as the correlation of those same numbers or of those same subjects when expressed in centimeters and kilograms. The correlation numbers should be the same. It is easy, because there are no units, it is easy to compare the strength of correlations, the strength of associations between different measures. We can, for instance, say that association between height and weight is stronger than association between age and weight, because we computed those correlations, those two correlations, and compared it together. If correlation number had units attached to it, it would be impossible to compare between different pairs of variables. The second pro of correlations is that correlations are understandable. General public typically understands or thinks that they understand correlations. We can use word correlations and correlation numbers in common language, and we don't get blank stares. However, correlations have many cons, and it's very important to be aware of them. So here is a first problem with correlations. When you look at those two scatter plots, which one do you think has a stronger correlation, correlation closer either to +1 or -1? So surprisingly, both scatter plots have correlation very close to 0, because the Pearson correlation measures only linear relationship, linear association between two variables. In both scatter plots on the slide, we don't have linear association. So the Pearson correlation as a measure of linear association fails. It says correctly that in the first scatter plot, the association seems to be 0. The data really seem to be randomly distributed on the page. But on the second scatter plot, we have a very strong quadratic nonlinear association between x and y, yet correlation coefficient says the association is equal 0. So correlation coefficient is a single number summary, a measure of linear association only. Like all single number summaries, it can give misleading results if not used with supplementary information such as scatter plots. We always have to look at scatter plots when we compute correlation coefficient. Especially in this case, low correlation close to 0, does not mean that there is no association between x and y, that there is no relationship between x and y. As we can see on the second picture, on the second figure, there is a strong association between x and y, but the association is not linear. So correlation close to 0 only says there is no linear association between x and y. So let's look at a second issue with correlation. Here we have so-called Ascombes quartet, and French researcher Ascombes put it together. So again, the same question. Which scatter plot expresses a stronger correlation? When you look at it, which scatter plot do you think will have a higher correlation value R? And it's a trick question. They all have the same correlation. They all have the correlation 0.816. I think they differ on a fifth digit. But again, correlation is a measure of linear association between x and y. So correlation as a coefficient is a correct measure only for the first scatter plot. The first scatter plot has a linear association between x and y, and correlation would be an appropriate measure. The second scatter plot has a nonlinear association between x and y. It's quadratic, and in this case, correlation will give us a misleading number. The third and fourth, they both have outliers in a different directions position, and you can see that it really strongly affects how we see or how we measure the association between x and y. So again, the same thing as we said before, like all single number summaries, it can give misleading results if not used with supplementary information such as scatter plot. In this case, it means that if we actually obtain a high correlation number, high correlation does not guarantee linearity. Just because correlation is equal 0.8 or 0.9 does not mean the data actually follow a linear association, and does not mean that we have something weird happening. We always have to look at scatter plot. Every single time the correlation coefficient is computed, a scatter plot should be inspected. So let's look at third problem with correlations. Here we have two scatter plots or two graphs on one scatter plot. We have red dots and blue dots. Which color dots do you think have stronger correlation? The blue or the red? Knowing that the correlation actually measures the spread around linear association around the line, we would think that the red dots have stronger association than the blue dots just because there is less scatter. But the problem is in the limits of the y-axis. Unfortunately, or as we can expect now, both of those relationships, blue and red, have the same correlation, 787, exactly. Correlation is a measure of linearity and scatter around the line, not magnitude. Here what is different between red and blue is actually the magnitude, the slope of the line. Because the slope is stronger or higher, larger in the blue dots, the red dots are actually they have much space on the y-axis and they're visually squashed. So we always have to check the scatter plot, and for purpose of correlation, each correlation needs its own scatter plot. we cannot combine them on different scatter plot, on one scatter plot. So what happens if I separate those two pictures, if I separate the red dots and blue dots and plot them separately? As you can see, they are exactly the same data. The only thing that differs between them is the magnitude of slope, but the spread around the line is exactly the same. The slope in the blue dots is faster or bigger than the slope in red dots, but they actually are the same measures in terms of association. So we always have to look at correlations separately. It is impossible to judge correlations and compare them when plotted on the same scatter plot. So last but not least problem with correlation is, what if we have scatter plot that looks like mess? Do you think there is a relationship? Is there an association in this scatter plot? So when we compute correlation coefficient for this particular data, we will get correlation 0.214. Some people might think that correlation 0.214 is actually quite a strong correlation. I've heard opinions that 0.214 is 1/5 between 0 and +1. However, that doesn't mean that we have a strong association. The absolute value, the magnitude of correlation, tends to overestimate the true association, the true relationship between X and Y. For instance, correlation that are 0.3 or less tend to look like a randomness, and we are not even able to judge whether there is a positive or negative association. Correlation larger than 0.7 start to look like meaningful lines. But what happens if I do hypothesis test about the correlation 0.214? What happens if I ask whether correlation 0.214 in this particular example is significant? If I compute hypothesis test, I have 96 data points in the graph. Then I will obtain a test statistic 2.14 with 94 degrees of freedom, and that will actually produce a p-value less than 0.05. So based on the data and based on the correlation coefficient, I would say that there is a significant association between X and Y on level of significance 5%. However, this association does not look meaningless. If you look at the picture, that association actually does not look as anything close to association. The problem with correlation is that any meaningless relationship, any relationship that is very close to zero and visually doesn't mean anything, could be statistically significant as long as n is large. So often with an n larger than 100, we see associations significant, but when we look at the actual picture, when we look at the scatter plot, the associations do not look meaningful. So we have to be very careful about interpreting statistical significant correlations as meaningful relationship. The only way how we can see them meaningful is actually to look at the picture. So we always have to look at the scatter plot first or after. So what if I would like to compute the relationship between height and weight adjusted by age? What if I would like to estimate association between height and weight as I did before, but this time I want to adjust it by age? In this moment, correlation coefficient, the Pearson correlation coefficient as we introduce it, does not work. Correlation coefficient can capture only linear relationship between two variables. If we want to adjust by another third or fourth variable, we actually have to utilize linear regression or any kind of modeling. So we have to run a statistical model. So here is a picture of 8 scatter plots, and which one do you think has the strongest relationship? Again, if we actually compute correlation coefficient for all 8 scatter plots, the correlation coefficient is 0.7. So without looking at the scatter plot, we do not know what caused the correlation coefficient 0.7. For instance, on a scatter plot 1, what we see is actually random noise data that have no association and one outlier in a right upper corner. So that creates the correlation 0.7. However, correlation coefficient for scatter plot number 1 is actually wrong measure of association. In a scatter plot number 2, we have exactly opposite. We have a perfect association between x and y, and one outlier that destroys the perfect association, so the correlation coefficient ends up being 0.7. Again, correlation coefficient as we compute it is not a correct summary of the association between x and y in scatter plot number 2. The same for scatter plot numbers 3, 4, and 5. The correlation coefficient is a proper numerical summary of association between x and y only for scatter plot number 6. For all other 7 scatter plots, it's a wrong association between, or a wrong measure of association between x and y. So when we compute correlation, and when we get that the correlation is 0.7, we can't be sure that our scatter plot looks like scatter plot number 6. It could be scatter plot number 1, or 5, or 8. We have to actually look at scatter plot. For every correlation coefficient, we should plot a scatter plot and look at the data. So what to do about the correlation magnitude? The correlation magnitude can be misleading. And second of all, correlation has actually no interpretation. If correlation is 0.7, there is no way to interpret the number 0.7 besides saying that correlation coefficient between x and y is 0.7. So there is a solution to those two problems. We can actually take a square of correlation. Once we take a square of correlation, what we obtain is so-called coefficient of determination. Coefficient of determination is new measure that has better interpretation, and it also behaves better as a magnitude. So here it is. Here I have correlation coefficients. I took them in absolute value, so either 0.1 or 0.2 or 0.3. They could be plus or minus. But when I square it, the plus or minus goes away, and we basically get a plus. So what will be r squared for 0.1? R squared for 0.1, correlation squared for 0.1 will be 0.01. Correlation squared 0.2 will be 0.04. So now we see that the correlation 0.2 that we actually found significant in a previous slide would have r squared coefficient of determination 0.04, which is much closer to zero, and properly describes the non-association, no meaningful association that we saw in the scatter plot before. Now you can see correlation 0.5 when squared is only 0.25. Correlation 0.7 when the data finally start looking like a meaningful line are actually squared 0.49. So coefficient of determination in this simple case is just correlation squared, and it's often denoted as r squared. It also has an interpretation. Coefficient of determination can be interpreted as proportion of variation in y that is explained by variation in x. So for instance, if correlation is equal 0.3, 0.3 squared is 0.09, so we can interpret it as percentage that 9% of variation in outcome is explained by variation in predictors. So what we can say is our subjects have a different outcome. For instance, the outcome will be weight. Our subjects have different weights. And if I square the correlation, that is the proportion of differences in weights that can be explained by our differences or the subject's differences in height. So that is very, very nice interpretation, and I highly encourage people to always square the correlations and interpret it as coefficient of determination. It makes it much more understandable to the public, and it makes the result not overestimating the actual association between X and Y. So we talk about Pearson correlation so far, but there are several different correlation coefficients. One of them is Spearman's correlation. Spearman correlation, or Spearman's rank order correlation, is another type of correlation commonly used in the research. It is actually a non-parametric measure of association between X and Y that does not depend on linearity. The Spearman correlation measures the strength of X and Y as a monotonic relationship between X and Y. Monotonic means that it has to be only increasing or only decreasing, but it doesn't have to be linear. So what is monotonic? Let's look at the first graph. The first graph is decreasing, and it's decreasing from the beginning to the end, actually linearly, and it is a monotonic function. The second graph also portrays monotonic function, even though it is not linear. You can see that as X increases, the Y increases more in a quadratic fashion. So in this case, we can also compute Spearman's correlation. Spearman's correlation can be computed where Pearson correlations fail. However, in the third graph, when X goes up and then when X increases, Y increases but then decreases. So there is a non-monotonic function. For half of the graph it increases and for half of the graph it decreases. In this case, Spearman correlation would be a wrong measure of association between X and Y. So the Spearman correlation coefficient is different than Pearson correlation coefficient. Often we say that Spearman correlation coefficient is non-parametric because it doesn't have the same assumptions, or the same assumptions don't need to be satisfied as for Pearson correlation coefficient, and it measures the monotonic relationship between X and Y. Pearson correlation coefficient measures the linear association between X and Y, but Spearman correlation coefficient measures the monotonic association between X and Y. So Spearman correlation coefficient is calculated not using the actual data values that we measured, but we determine rank of every observation between X and Y, and the formula then uses the ranks instead of the magnitude of each observation that is measured. So outliers are not affecting Spearman correlation as much as Pearson correlation, because the outlier is not really measured by its value, but just by the rank inside the data. So let's look at some examples. Spearman's rank order correlation is useful often because it makes no assumption about the distribution of the data like Pearson does, normality, and can be used when Pearson assumptions are violated, or when we don't have enough data to actually make sure that Pearson assumptions are satisfied. Spearman's correlation can be used when there are few data points. So we just need to have monotonic association. And it's less sensitive to outliers because it's only measuring or only accounting for the rank of the data points, not the actual value. So here are some examples. Looking at the scatter plot is always the most important. So for instance, in the first scatter plot, as you can see, we have a monotonic relationship. As X increases, Y increases, but that relationship is not linear. That's why Spearman correlation correctly portrays the relationship as 1, because the relationship has no scatter around the nonlinear line, but Pearson correlation fails, and Pearson correlation says that it's a 0.8. Pearson correlation captures linearity, and there is no linearity in the data, so that's why it is a wrong measure of association between X and Y in this example. Spearman captures only monotonicity, and that's why it is a proper measure of association in this example. Here in the second example, we actually see sort of random noise in some elliptical fashion. And in this case, it's very hard to judge whether the data are linearly or monotonically associated. They look monotonic because as X increases, Y somewhat increases. And in this example, actually, Pearson and Spearman correlation will both lead to very similar results. Both will estimate the relationship as not very strong. In the last example, we see quite a strong relationship between X and Y with some outliers. In this case, again, Pearson correlation is better measure of association between X and Y because it cares only about monotonicity, while Spearman correlation is better measure of association between X and Y, while Pearson correlation requires linearity, and the outliers are destroying the linearity between X and Y. So last piece I want to talk about is how to visualize correlations. In nowadays age, we can compute hundreds and thousands of correlations, and plotting the correlations is always more preferred than creating a tables of hundreds or thousands of correlation summaries. So when using Pearson or Spearman correlation, visualization might be challenging, and there are ways how to visualize nicely correlations. In many cases, we have large number of variables and large number of correlations, and we need to somehow maybe plot them rather than create tables. So I found a really nice paper that shows Spearman's correlation values for 94 chemicals in the home using a heat map approach as also as a modified scatter plot approach. So here is the paper. The paper has a title, Persistent Organic Pollutants in Dust from Older Homes. And it basically was based on the abstract, as you can see. The aim was to evaluate the relationship between home age and concentration of multiple chemical contaminants in settled dust and discuss the feasibility of using lead hazard controls. So for evaluating the aim, they actually computed a lot of correlations between the age of the homes and the concentration of different contaminants. As you can see from the methods, they actually collected dust sample from 583 homes and analyzed samples for 94 chemicals. So they have 94 chemicals that they measured in those 583 homes, and they want to see the association with age. So for just A1, they will have 94 correlation numbers. They also were interested how the chemicals are related to each other. And because they measured 94 chemicals, they could have 94 times 93 divided by 2 associations between all those 94 chemicals. So that is a lot of correlations to plot. They decided that they will consider correlation to be meaningful and significant if it's larger than 0.2. You can see that that means that p-value is less than 0.001. And they decided that because of the multiple comparison issues. So here it is. On this picture, you can see a heat map of correlations between those 94 chemicals. The 94 chemicals are grouped into meaningful groups. So the first several correlations are between OC insecticides. The next one are OP insecticides, and so on. Now, correlations that were positive have actually sort of yellow to red color. Correlations that were negative are in bluish colors. And you can see on that heat map that we have a red, very strong line diagonally from upper left corner to bottom right corner. That line is actually consisting of correlation equal 1 because a variable correlated with itself will always have correlation equal 1. So in this correlation matrix, on the diagonal, we have correlations of that particular variable with itself. So that must be equal 1. But next to it is a correlation, for instance, of that particular variable with variable next to it, variable either above or below the same row. So you can see that some of those correlations are quite close to 1. Additionally, they created a histogram of those correlations and plotted it in the other triangular in the matrix. So we can see that we have two correlations that are between -0.4 and -0.2. Those two correlations will be dark blue, and we can see them somewhere in the metals and OP insecticides and carbamate insecticides. So those are those two negative correlations that say if one of those chemicals is present, the other one is less likely to be present. Strong positive correlations are, for instance, among PAHs. So if you look at PAHs, you see that there is sort of a triangular that is quite yellow and red. And that means that if we see one of those chemicals, the other ones are very likely to be present also. The same about tobacco markers and PBDs. So that is actually a really nice way. The heat map is the modern way how to portray correlations between many variables together. Instead of correlations, we just transform the correlation into a color and basically portray it with color. We can also make the color stronger for a significant correlations if important, or we can put a little star. Then second, what they wanted to do is actually portray the correlations between the 94 chemicals and the age of the home. So at this point, we will have only 94 correlations, but what we want to do is actually compare them to each other. Even creating a table with 94 correlation numbers would be hard. Additionally, what we want to highlight is that correlations that are larger than 0.2 are significant or meaningful to us. So this is what they did. They put the chemicals on an x-axis, again grouped and color-coded for nice understanding, and then the correlation for that particular chemical and age of the home is plotted on the y-axis. So you can see that the first OC insecticides has actually the highest correlation of 0.6, and that first one is actually DDT. Additionally, they plotted a line at 0.2, so we can easily see those correlations that are higher than 0.2 and thus considered meaningful or significant. So you can see that those permanent rank correlation coefficients between age and chemicals are plotted in a very understandable fashion, color-coded, and yet we can very quickly see which of those chemicals is the most correlated with the age of the home, and which of those correlations are significant and meaningful, what authors consider meaningful, and which ones are not. So I find these two examples very nice examples of plotting correlations to make it understandable to reader and also portray a lot of information. I hope this small lecture was helpful, and thank you for listening.